So up until this point, we've learned about 3 different ways that a quadratic relation can be expressed. It can be in vertex form, standard form, or intercept, or we call it sometimes factored form, and that there are pros and cons of each form in terms of the information it gives you about its parabola. And up until now, we've sort of dissed standard form because really the only thing that it could give us is the value of the y-intercept, if we allow x to be 0, and the a value could tell if it's upward, downward facing, and whether it's been stretched or compressed. But it couldn't give us any other details like the coordinates of the vertex or any of the roots or x-intercepts until now. In our previous video now, we've learned that standard form, if we use the a, b, and c values in front of the x squared, x, and non-x terms respectively, can be plugged into the quadratic formula to find the roots, where the roots are equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's great. Now it gives us roots, gives us y-intercept. Could it give us vertex? Well, there is another little thing that we can add to our toolkit that doesn't maybe give us the vertex directly, but it does give us the value of the axis of symmetry. And this little tool is as follows. It's negative b over 2a. It's like, what? All we gotta do is take the b value, sub it in, and the a value and sub it in. And I'm like, yeah. And then once you have the axis of symmetry, you know that that is your x coordinate of the vertex. And you know that you could just sub in this value into the equation where x is to get the y value of the vertex. Okay, so standard form actually can give us a lot of information about a parabola. Maybe not as directly as these two, but through a little bit of work. And we learned in the last video how much work that one can be sometimes. But this is a really neat little new tool that I want to introduce you to. And we're going to use this example to show you it. So I just need to erase this for space, but we'll come back to it and put it into practice. So let's say that you are given an equation of y equals 2x squared plus 5x minus 12, and you're asked to sketch it. So sketch it means you want to show as many of its key features as you can, but it doesn't have to be done on graph paper. It can just be drawn and important points can be labeled. So what might some of those important things be? Well, obviously you'd like to do the x-intercepts or the roots. You'd also like to maybe show the axis of symmetry. I'm going to call it the A of S, which of course leads you to showing the vertex. And if you like, even as one more little bonus, you might be able to show the y-intercept as well. And these are all the key features that you would include in a sketch. So how can we, from this equation, get all of those key features? Let's explore some options. Well, when it comes to finding the roots, ideally, we'd like to try and factor it first because factored form allows us to find the roots very quickly. So let's see if we can factor this. Our first question when we are asked to factor is there a GCF? And clearly there isn't in this case. And then because it's a trinomial, we might ask ourselves, is this a perfect square trinomial? Well, neither the first term nor the last term, when we write them in descending power of x, are perfect squares. So automatically it fails 2 out of the 3 tests without even trying the third test for a perfect square trinomial. So then we would ask ourselves, well, are there two numbers that multiply to give a times c, which is negative 24, and add to give the value of b, which is 5? So some factors of 24, I'm going to have one of them positive, one of them negative, to multiply to give a negative number, but the larger of the two will be the positive one. So, 1 and 24, there's no way that adds to 5. Let's start getting these a little closer. What about 2 and 12? Closer, we're at positive 10 instead of positive 24. What about 3 and 8? Ah, there we go. So we can factor this. Now we can either use Berry method or split the middle term. So let's find the roots. We're going to set this equal to 0 because, of course, y is equal to 0 when we're looking for roots. And where I have plus 5x, I'm going to use 8x and negative 3x instead. And it doesn't matter which order they go in. I'm going to put the 8x first and 3x second, just because I think 3 and 12 have a few more things in common, and 2 and 8 do. And it honestly doesn't matter. You'll get the same answer either way. To factor by grouping, then, we take the GCF out of each pairing of terms. So here I have 2x. I'm left with x plus 4. And over here, I know I have to, again, be left with x plus 4. There has to be a common binomial here when we factor by grouping. So what factor has to be taken out? It has to be negative 3. So let's take out that binomial common factor of x plus 4 times 2x minus 3 equals 0. And then we can set each of these equal to 0 to see what the two roots are. So x plus 4 equals 0 means that x could be negative 4. And 2x minus 3 equals 0. If I rearrange for x, I'll get 2x equals 3. Divide both sides by 2, x would be 3/2. So there are my roots by factoring. Now, just for fun, you could also use the quadratic formula. Okay, and this would be your a value, because it's the value in front of the x squared term. This would be your b value, because it's in front of the x term, and this would be your c. And you should get the exact same answers using both the positive square root of the discriminant option and the negative square root of the discriminant option. Okay, but we found both of those. I'm going to make a little list here of the values I'm going to be putting on my sketch, because I'm going to need to erase some work in order to do the sketch. So I've got x equals negative 4, I've got x equals 3/2. All right, so next on my checklist, I want to find the axis of symmetry. Now there's two ways I can do that. Before this lesson, you know that you could average these two intercepts and find the middle of them. So let's try that. So x for the axis of symmetry is negative 4 plus 3/2. I'm adding them and dividing by 2 to find the middle. So I need these both to have a common denominator, so they're the same size. This becomes negative 8/2. This is 3/2 over 2. This becomes, I'm just going to write down here for space, negative 5/2 divided by 2. Notice what I just said and how I wrote it, which is the same as negative 5/2 times 1/2, or negative 5/4. Okay, so again, I'm going to add this here, that my axis of symmetry, I'm going to call it A of S, is negative 5/4. Now you can see that when these are not integer values, this works, but it's maybe a little bit more work than maybe if we use our new tool. We could also do that x for the axis of symmetry can be taken from standard form. It's equal to negative b over 2a. So let's try this and see what happens. Our b value is 5, so negative b would be negative 5. And double our a value is 2. Look at that, negative 5/4. So it comes out to the exact same answer, but this sure is slick for finding the axis of symmetry when you're given it in standard form, right? So I wanted to show you that so that you have that as another tool. All right, so going through our checklist of key features, we've got the first two. Now we need to find the vertex. So to find the vertex, I need to sub in that x value for the axis of symmetry into the equation and see what y is equal to. So let's do that. Y for the vertex, whoops, let's try that again, is equal to 2 times the x value for the axis of symmetry, which is negative 5/4, quantity squared, minus 5 times negative 5/4, plus 5 times negative 5/4, minus 12. So when I see this, multiplication does not come ahead of exponents. According to BEDMAS, exponents must come first. So this really means negative 5/4 times negative 5/4. I'm going to be explicit here and show you this so that you don't make this mistake. It means that you have to multiply the tops together and the bottoms together. So that comes out to 25 over 16. A common mistake students make is they'll square the numerator, but they won't square the denominator because they don't realize what this notation truly means. And then I'm going to do 5 times negative 5/4, which is negative 25 over 4. This has a denominator of 1, so same idea, multiply the numerators and the denominators together, minus 12. Here I'll just finish multiplying by 2, so that becomes 50 over 16 minus 25 over 4 minus 12. Now you might go, yuck, how can I do this? Don't run to your calculator just yet. You can do this. These are all different sizes. This is sixteenths, quarters, and wholes, but we can make them all the same size and then we can add and subtract them. Let's make them into the smallest size, which is sixteenths. So in order to make this one into sixteenths, I would have to multiply the denominator by 4. And whatever I do at the bottom, I have to do the top. So this becomes 100. And then similarly here, this is 12 over 1. If I want it to be sixteenths, I have to multiply the denominator by 16. So let's multiply the numerator by 16 as well and make 192. So 292 of these sixteenths are negative, 50 of them are positive. That means that I have more negatives than positives. In fact, I have 242 more negative sixteenths than I do positive sixteenths. I'd like to reduce this down because I'm going to be graphing it. I notice that they're both divisible by 2. Let's see what happens if we cut them in half. Made up with 121 over 8. 121 is a prime number, so we're done. At this point, if you want to kind of know what that's going to look like when you sketch it, you could punch this into your calculator. I'm going to tell you it ends up being about negative 15, and it's 0.125, so 15 and an eighth. Okay, so on my list of things to include as features for the parabola, I'm going to add the vertex. And the vertex is going to be negative 5/4 and negative 121 over 8. All right, the last piece that I could include when I'm sketching this parabola is the y-intercept. Well, the y-intercept is great because we can just take it from standard form. And the reason we can do that is that x is 0 for the y-intercept. So this term is 0, this term is 0, this is the y-intercept. So that would mean our y-intercept is negative 12. So I'm just going to put that in here too. We've got a y-intercept of 0, negative 12. All right, let's put all of these pieces together in a sketch. So I've noticed that the coordinates of my vertex are both negative, so they're going to be in the bottom left quadrant. So maybe when I do my sketch, I'm going to leave some space for that vertex to be down here. Okay. Again, this doesn't have to be on graph paper. It doesn't have to be to scale. Negative 5/4 is just a little bit more than negative 1. So, you know, maybe something like this. Negative 5/4, negative 121 over 8. There's the vertex. I could add in my axis of symmetry here. Right? And up here I could say x equals negative 5/4. Okay, so there's two of the things I need to show. I need some x-intercepts. One of them's at 3/2, so a little bit more than 1, so maybe here. And I'll just write it as 3/2, 0. The other one's at negative 4, so I don't know, maybe somewhere over here. Okay, and I've got a y-intercept at negative 12. So this is not going to be surprising when we go to draw in this curve. It is going to hit the y-axis, and we can label that as 0, 12. And look at that, all your key features. You got your x-intercepts, you got your vertex, you got your axis of symmetry, and you got your y-intercept. And we got it all from standard form, which is really great. It takes a bit more work to get it all from standard form. I mean, vertex form gives us the vertex by inspection, and intercept gives us the intercepts by inspection. But nonetheless, we can get some things from standard form too, if it's easier than trying to convert one way or the other. If this isn't factorable, or we don't want to complete the square. And there you go. The beauties of the quadratic formula, and also of pulling out key features from standard form.